Okay, so here's another example that's a little bit simpler than the last one. We are going to make it a little bit more complicated later. We have a car. Here's its mass. It's traveling at a constant velocity of 23.5 meters per second. It's really good to maybe highlight or underline as you're reading questions through to try to start picking out useful information. I see that the engine moving the car is applying a force. Here's the force. What is the force of drag? The force of drag that's opposing the motion. What is the size of that force? Okay, so I think I have a good grasp of the question. We're going to do what we always do here. We're going to model our scenario. So here's my dot representing my car. I now want to draw all forces acting on it. So the first force that we may want to draw would be the force of gravity pulling it down. I might be tempted to go ahead and calculate that, but I'm not sure if I need to, so I'll just hold off on that. Now I want you to think about this. If you have a car on the road, gravity's pulling it down, your car is not accelerating down, crashing through the earth somehow in free fall. So what other force must be acting on the car? Yeah, there's got to be a force up, right? An equal force going up the other way. In other words, the forces up and down on this car are balanced. So really, I'm not actually worried about them. I could call that the contact force. Sometimes it's called the normal force, F of n. You may see that whenever an object is resting on another surface. Sometimes it's called the normal force. To stay consistent, I'm going to use the term contact force. So those forces in the up and down dimension, the vertical axis, would be what I call balance. They're equal and opposite. The car is not floating off the ground. It's not crashing through. It has no upward or downward acceleration, so those are balanced. I'm going to have a force coming off here to the right. I'm going to maybe call that the force of the engine or the force of push or something like that. And I know that that equals 2.7 times 10 to the third newtons. Once again, we weren't worried about the size of these up and down forces because we know they cancel out. We're not being asked about them. And I know that there's a force of push coming from the motor, and opposing the motion, going back the other way, there is a drag force. And I'm being asked to find that drag force. What is it going to be? Well, is there anything else that we know that I forgot to write down? A lot of people miss this, and a lot of people want to go straight away and say, oh, well, the acceleration is 23.5 because that number is right here. Is that true? No. The car is moving at a constant velocity. What is true about acceleration? Remember, forces always deal with changes in velocity, changes in motion, acceleration. What's true if the velocity is constant, if it's not changing? If you have no change in velocity, if your velocity is constant, then guess what? Your acceleration is also zero. This car is not accelerating up or down, we knew that already, and it's not accelerating to the left or the right. So what does that tell you about these two forces if the acceleration is zero? It tells you they have to balance each other. If this is a force going to the right with this size, 2.7 times 10 to the 3 newtons, guess what that drag force has got to be? It's got to be the exact same size, 2.7 times 10 to the third newtons, in the other direction, negative, going back to the left. We could show this more thoroughly mathematically if you wanted to by using our Newton's second law equation. The sum of the forces equals the mass times the acceleration. I know the mass of the car. It doesn't matter though because what's the acceleration? Constant velocity, the acceleration is zero. So I know that the sum of the forces is going to equal zero. Anything times zero is zero. What forces are involved in this sum? Whenever you are adding up or summing forces, you can only do that for forces that are in the same axis or the same dimension. So I cannot do this. I cannot say the force of contact plus the force of gravity plus the force of push plus the force of drag equals 0. I can't do that because these two forces right here are working in an opposite dimension from these two forces. They are not speaking the same language. In other words, these are up and down, these are left and right, so I cannot do that. The sum of the forces there is referring to forces that are working in the same dimension. So I could say this. I could say, okay, the force of push is 2.7 times 10 to the third. And I know that that plus the drag force has got to equal 0. How do I solve for that drag force? Well, I have to subtract this away from both sides. So I'm going to get the drag force equals negative 2.7 times 10 to the third. Never forget your units, newtons. Exactly what we found here just by thinking about it. These forces have to be balanced because the acceleration is 0. Let's make it a little bit more complicated now. Okay, so here's a new question I'm asking. If the drag force now remains the same, but the engine now applies a much larger force, 4.1 times 10 to the third newtons, what will the acceleration of the car be now? So once again, we're always going to start by creating a model. Here's my car. I know there are up and down forces. I know that they're still going to be balanced, so I'm not really worried about those. Let me leave those out of my diagram for now, just for simplicity's sake. And I know that the force of push coming from the engine is now 4.1 times 10 to the third newtons. And I know that the drag force opposing that, I need to draw a little bit shorter because it's a smaller force. It's the same as it was before, 2.7 times 10 to the third newtons. You can go ahead and call that negative here if you want to in your diagram, or you can just recognize that, hey, left is negative, and let that tell you. I know that the mass of the car also is 4,200 kilograms. So there's everything I know. You will always start every problem this way. Make a model, this is what you know, this is what you don't know. I don't know the acceleration. Could you look at this, by the way, and predict in which direction the car's acceleration will be? Yeah, the car should be accelerating to the right. If the car is moving to the right, positive velocity and positive acceleration, then we know that the car should be speeding up. How do we know the accelerations should be positive? Because look at the forces. Where's the larger force? To the right. These forces are no longer balanced. These forces are unbalanced. And this one is larger, so it's going to win out, causing the car to accelerate to the right. I want to calculate that acceleration, so I have to use Newton's law. Remember, I'm trying to find something, a tool, an equation that will help me take all of this and find my answer. Sum of the forces equals mass. Sum of the forces equals mass times acceleration. What does this tell me to do? It tells me to take my forces and add them up. So I'm going to get a positive 4.1 times 10 to the third plus minus 2.7 times 10 to the third. I'm just going to call that minus 2.7 times 10 to the third. So there's my sigma f, my sum of the forces. So I've expanded the left side of this equation. If I solve that, the sum of the forces is going to give me a number. 4.1 times 10 to the third minus 2.7 times 10 to the third. Here's a quick trick about scientific notation. If both numbers are times 10 to the same power, you can just go ahead and subtract the numbers here. So 4.1 minus 2.7 is 1.4. So that's going to be 1.4 times 10 to the third. Am I done? Is that my answer? No. What have I just found? I found the net force. I found the total overall sum of the forces. Remember, that's like this. I have this larger force, which is 4.1. I had a smaller force, which was 2.7 the other way. So how much left over do I have? Well, this force pointing to the right is larger, so there's my leftover force of 1.4. That's my net force, right? Times 10 to the third, obviously. So that's my net force. That's the sigma F. So I can say 1.4 times 10 to the third equals ma. Do I know what the mass is? Yes, I do. I wrote it down in my diagram. The mass is 4,200. How can I solve for a? Divide by 4,200 on both sides. If you're not familiar with scientific notation, your calculator should have a button that says EE. It's I think it's second 7 if you have a TI. That EE means times 10 to the power of. So if you type in 1.4, hit the EE button, it'll show up as an E on your screen, and then hit the 3. That's the same thing as this. Or you could just type that into your calculator. Or you could take it out of scientific notation. Maybe we should practice that. We've not practiced that yet. This means to multiply this times 10 to the third power times 1,000, a 1 with 3 zeros. Really what that's telling me to do is take this decimal, move it to the right 3 times. So there would be moving it 1 time, 2 times, 3 times. So 1,400, 1,400 equals 4,200. A, divide both sides by 4,200. I'm going to get a positive acceleration. That's what we predicted, right? My net force is a positive number. So the acceleration due to that net force, remember net forces cause acceleration. The acceleration due to that net force is also positive. 4,200 divided by 1,400. I'm going to have an acceleration of a nice, neat, even 3. Never forget your units, meters per second squared. This acceleration is positive. It was moving with a positive velocity, positive and positive. They agree with each other, so that car is now speeding up.